Hi, welcome back. In the previous video, we introduced the idea of a transmission line, particularly a lossless transmission line. In this video, we're going to look at the details now. So I want to remind you that a lossless transmission line is one in which all of the source power makes it to the load, and there's no loss in power on the line itself. And we're only going to talk about lossless transmission lines in our course. Such a line can be modeled. As we said, we're going to distribute the inductance and the capacitance like this. So we've got these inductors and capacitors, but we're modeling the line like this, but we have no resistors because we're saying the line is lossless and resistors absorb power. So we're going to model our transmission line like this. This is to say, we're not saying here that there are actual inductors and capacitors on the line. We're saying the line itself has these parasitic capacitances and inductances. So now let's say the line is oriented in the z direction, and so we're going to call this in the middle here to be z, and we're breaking this thing into discrete segments. So this is z plus delta z and z minus delta z over there, and we're going to say the voltage here is v of z, right? And then the current going into the node is I of z. And remember that those capacitances are distributed, so they're the capacitance per unit length and the inductance per unit length. So we can write a KCL equation at this node, and to do that we would say that the current going in, and I'm going to show the time dependence here, I of z of t is equal to the current going through the capacitor, so that current is C dV dt, remember from circuit analysis. So the capacitance is the per unit capacitance times delta Z, that's the total capacitance, then dV dt, plus the current that leaves to the next node, right, like this. That's Kirchhoffs' current law, and if we rearrange this just a little bit, hopefully you notice that the thing that I'm drawing right here on the left of the equation is a difference quotient. And you should know from calculus that a difference quotient means something very nice. Here, we want to take the limit as delta z goes to 0 because we're saying that this line is a continuous line. We don't want to break it into these discrete segments. We want to consider a truly distributed line, continuously distributed. So we're going to take the limit as delta z goes to 0, and you know from calculus that a difference quotient, when you take the derivative, or when you take the difference going to 0, then you get a derivative. So this is a partial because we're taking the limit as z goes to 0, not t. A partial with respect to z is equal to this thing here. So this is telling us that the spatial derivative of I is related to the time derivative of v with this negative c hat. We're going to call that equation 1. And similarly, if we did Kirchhoffs' voltage law around the loop, which we're not going to do, but you can try it out, we could show that the spatial derivative of v is related to the time derivative of I, like this. And we're going to call that equation 2. And equations 1 and 2 collectively make up what's known as the telegraphist's equations. Now, if you take equation 1, let's say, and you differentiate it with respect to time, I'm going to drop the dependence here. I'm just going to say d squared I. Time derivative, so we have dt dz, is equal to negative c hat d squared v dt squared, like that. And then if you take the z derivative, the spatial derivative of equation 2, then you get dv squared dz squared equals negative L hat d squared I dt dz. Now you can see how these two are linked. You can plug this in for d squared I dt dz, right? And so when we do that, we get d squared v dz squared. We've eliminated the I now, so this becomes L hat C hat d squared v dt squared, or in another way, written in another way, if we bring that over to the left, we've got minus L hat C hat d squared v dt squared equals 0, and we recognize that hopefully as a wave equation, right? This is a wave equation, and we could alternatively write it in terms of I instead of V. So I also satisfies a wave equation, and we recognize from the wave equation that this is related to the wave speed. The wave speed is 1 over the square root of L hat C hat, if you recall that from our discussion of wave speed. And then being that the wave speed is omega, the frequency, over beta, we have beta is equal to omega times the square root of L hat C hat. Nice. And remember that the wavelength is related to beta by 2 pi over beta, like this. Okay, good. Now, let's assume a time harmonic dependence. And if we do that, equation 1 here, if remember taking the derivative in time is like multiplying by j omega in frequency. So I'm gonna write this in a different color. So we would have d. I guess if we're assuming a time harmonic, then the time dependency would drop out. So we would have dis. So I'm writing this in the phasor domain now. Times j omega vs. Right, so this is what equation 1 would become if we assume a time harmonic dependence. So we're just going to keep that in mind. I'm going to give myself some space here. I'm going to erase some of this. Okay, so being that we're assuming a time harmonic dependence, and being that we have a wave equation, remember that the solution to a wave equation is, in general, a wave that's traveling to the left and to the right. So this is the wave that's traveling to the right, and then this is the wave that's traveling to the left. And I'm using V0 plus and V0 minus to represent the amplitudes of those respective components. And similarly, since we can have a wave in the current also is going to be a wave like this. So what kind of wave are we talking about, right? If we send a DC signal down this transmission line, what kind of wave are we talking about? Well, remember we said in the previous video that there's going to be a reflection at the load, and so that reflection interferes with the DC that's being sent, and so that's kind of the wave that we're dealing with here. That interference between the reflection and the transmission. So we've got these amplitudes V0 plus, V0 minus, I0 plus, I0 minus. Okay, and from this guy now in blue, or actually let's just keep that in mind. But let me take the time derivative here of this equation that I just wrote down for I. So if we take the time derivative of that, what we see is that well, we would get negative j beta I0 plus e to the minus j beta z plus j beta I0 minus e to the j beta z. Okay, that's the time derivative. And we know from this thing in blue that the time derivative is related to Vs like this. So this would become equal to minus j omega c hat, right, times Vs, and Vs is up top. So we've got perfect, right? Now we can simplify a few things. We can cancel, but let's see, did I do that right? Yep. Let me just check my notes, make sure that everything works out nicely. Okay, everything is good to go. Okay, now So we've got this relationship here after taking the time derivative. So we've got the relationship between the amplitudes of the current and the amplitudes in the voltage. The characteristic impedance of the line. So we're gonna denote what's called the characteristic impedance as Z naught. Characteristic impedance. It's defined as the ratio of the positively traveling voltage to the positively traveling current at any point on the line. That is to say, Z0 is V0 plus over I0 plus at any point on the line, given that I0 minus and V0 minus are 0. So we're just kind of ignoring I0 minus and I0 plus. So if you look at this equation here, and you set I0 to be I0 minus to be 0 and V0 minus to be 0, and you look at this ratio of V0 plus to V0 to I0 plus, you'll see the J's drop out and so forth, and what we get is beta over omega c hat. Right, so convince yourself of that. And then this can be using these relationships here, which I've erased a little bit. This was the wave speed. This was lambda. Using these relationships, we can write this as the square root of L hat over C hat. So this is the characteristic impedance of the line. Now, the cool thing to help you understand what the characteristic impedance is telling us, the cool thing is that it plays the same role as the intrinsic impedance, eta 0, for media, different media, right? We've already seen how intrinsic impedance can affect wave propagation. And so that's really what you want to think of for the characteristic impedance. That's how that's going to affect the voltage and the current in the same manner as the intrinsic impedance affected the waveform in media. And also you might ask, well, why did we set I0 minus and V0 minus? What about those guys? Well, if we did the same thing, if we took the ratio of, I don't want to say Z0 is equal to this, but if we looked at the ratio of these guys with V0 plus and I0 plus equal to 0, what you would get is negative beta over omega c. And the negative here just means that we're talking about the wave traveling to the left. And so really you get the same magnitude. So it doesn't matter if you look at the positively or the negatively traveling waves, you get the same magnitude. And so the characteristic impedance we just use as the positive one. So the characteristic impedance will always be positive. All right, so remember in the previous video that we mentioned 3 different or common types of transmission lines. There was the coaxial, and there was the microstrip and the twin lead. And I'll just remind you that here's our coaxial, and we're saying that this thing has a length of delta z, and it's got an inner radius of A and an outer radius of B. So this is the coaxial case, and we talked about the distributed capacitance and inductance. And so I guess I'm going to write that out again. Okay, that was the distributed capacitance. This was the distributed inductance. And the neat thing here is that if you want to look at the wave speed, remember the wave speed was 1 over the square root of mu times of L hat times C hat. And so if you do this multiplication of L hat times C hat, you'll see a lot of nice things happening, a lot of things canceling, and actually you just get mu epsilon. So the speed the speed of the electromagnetic wave in a coaxial cable is just 1 over the square root of the cable's permittivity times the permeability. And if we wanted to look at the cable's characteristic impedance, right, that was, what did we say, the square root of, I erased it unfortunately, that was Z0 was the square root of L hat over C hat. Okay, so if we look at that here, what do we get? So if I plug in L hat and then I divide it by C hat, you'll see again a lot of things canceling, and we get the square root of mu over epsilon times the natural log of B over A, like this. Okay, and if we looked at the microstrip line, remember the microstrip was another type of transmission line. Let me just try to draw that. Okay, and we said in the previous video, and we've derived these things, that the distributed capacitance was this thing, the distributed inductance was this thing. And so if we look at the wave speed, remember the wave speed was 1 over the square root, I'll write it up here, 1 over the square root of L hat C hat. Remember that? Okay, so what do we have here then? We've got, if we take L times C, you'll see a lot of nice things happening. Again, the D cancels, the W cancels, and again, we're left with 1 over the square root of its permittivity times its permeability. So the speed in a microstrip line, the speed of the wave, is the same as the speed of the EM wave in the coaxial line. And we wonder, well, what is the intrinsic impedance of a microstrip line? And again, we just found that this is the case. This is L hat, square root of L hat over C hat. So if I take L hat and if I divide it by C hat and I take the square root, what we end up getting is, looks like this here, the square root of mu over epsilon times d over w. So the geometry of the line is playing a role in the impedance, you see, but the speed is completely independent of the geometry of the line. All right, now then there was another one that we mentioned in the previous video, that was the twin lead, where we said the diameter was 2a, the separation distance was, I guess I should label this, I'm sorry, let's go back to the microstrip. This was distance d and this was distance w here. Sorry about that. Okay, so if we go to the twin lead, we were saying they were separated by a distance d, and they had each lead had a diameter d of 2a. So here we said that the distributed capacitance was pi epsilon over a hyperbolic cosine inverse of d over 2a, and then the inductance was mu over pi hyperbolic cosine inverse of d over 2a. And so again, if you want the wave speed of a electromagnetic wave in a twin lead, 1 over the square root of L hat C hat, you'll see a lot of things cancel here, and you get, again, the same speed. So the electromagnetic wave travels at the same speed in each of these 3 transmission lines. It's independent of the geometry, the speed that is. And if we looked at the intrinsic impedance, okay, if we looked at the the characteristic impedance, I still have media on my mind, but if we looked at the characteristic impedance of the twin lead and we calculated the square root of L hat over C hat, what we would get, looks like, is again the square root of mu over epsilon, but then times the geometry, something related to the geometry of this thing. So the geometry affects the characteristic impedance, but not the wave speed. Okay, so that gives you an idea of how the electromagnetic wave travels on the transmission lines. And next we're going to look at the source or the load end. What happens at the load end? So now we're going to bring in the reflections and the transmission coefficients into play here, or just the reflection coefficient. I'll see you in the next video.